Hi everyone, and welcome to this IAPSE webinar. We're already almost 50 attendees in place, but let's give it another few minutes before we kick off with these very interesting presentations of today. Okay, well, let's begin. I will just start with a short introduction to IAPSE, who we are, and we're an engineering society with a mission to exchange knowledge and advance the practice of structural engineering worldwide. We are present in over 100 countries, and we deal with everything within structural engineering. We do that organizing conferences. We have our own journal, Structural Engineering International. We have technical groups that publishes books and articles on relevant subjects. We have national groups in many of these 100 countries where you can network with other peers. And we have a program for young engineers, and we have annual awards. And a bit more on the national groups and webinars, which is one of the things we do to exchange knowledge. You can see all previous webinars on our website. This is an interesting one on existing structures as well. And I should also let you know that this webinar will be recorded and can be found on the IAPSE website after today. And then a few notes on some of the activities we have in the years to come. There is a conference in Ghent, or a congress in Ghent, in August. And I should let you all know that the early bird sign up has been prolonged a bit, so you can still make it with a discount. And for the IAPSE Symposium in Copenhagen in 2026, we have gathered a lot of abstracts for that. If you have a good idea, don't hesitate sending in an abstract. I think there is still a chance that it can be accepted, so don't hold back. I think that was it for me, and now I will leave the floor to Johan and Pau, who will present about the little built bridges in Denmark. which is the theme of today. As you see on the background photograph, Pau was so friendly to put up a picture from the Little Bell Bridge, suspension road bridge, and in the background you can see the Little Bell Bridge of 1935, almost 90 years old, which Johan will start her presentation on. So please, Johan, take it away.
Thank you, Jan. Yes, today I will share some of a little bit of insight in the probabilistic analysis that we did to update the characteristic train load for the Little Bell Bridge from 1935. This study was originally performed for a railway network Denmark in order to reassess the bridge, mainly for a new service platform, but also in order to update the probabilistic analysis, which they have a rule that should be updated every 25 years. So a little about RAMBLE in short. RAMBLE is a multidisciplinary engineering company. We have more than 18,000 experts around the world in more than 35 countries, over 300 offices. We are founded and have headquarters in Denmark in 1945, and we are a foundation-owned company. So the Little Bell Bridge, that's old riveted steel girder bridge that connects Jutland and Funen in Denmark. For this reassessment, we got a lot of traffic data from Railway Network Denmark that was recorded at a station in Bred, located on Funen. But it's safe to say that almost every train that passes this measurement station also passes the Little Bell Bridge. So we took that as one-to-one. Another nice picture taken from the Little Bell Bridge. As I said, it's a riveted steel girder bridge built in 1935. It carries 2 tracks of railway traffic, 2 lanes of road traffic, and a combined bicycle and walkway path. It has around 60 to 70 train passengers every year. It should also be said that it's the main bridge or carrying train traffic from Germany to Sweden and so on in the Nordics. A little bit about the traffic data that we have. Well, we have almost 5 years of traffic data from the measurement station. For each train that passes, we have a unique train ID. We have a timestamp for each axle. We have axles per train. We have weight of each axle. We have the speed. We have the direction of the train, and we have the train type. So here you also see some of the train types. On the top, you see most of the passenger trains. Then we have the locomotives. And then in the bottom, you can see the types of freight trains, wagons that you can experience on the bridge. Yes. So around these 60 to 70,000 train passes every year. It's almost equal in the eastbound and the westbound rail, you can say. It has more than or around 1 million axles in each direction. Yes. So to give you a little bit of insight in what kind of data we were dealing with, then I just plotted all the train type that was passing the Little Bell Bridge for a given year that we saw, and then the height spikes that you see, that's the passenger train. So that's the most common one you see. And then you have a lot of different types of freight trains that passes the bridge. So some of the things that you could also look at was the distance between axles. So that varies quite a lot, between almost no distance between the axles to quite large distances per axles. Then we also have the axle load, which also vary depending very much on if it's a freight train that's loaded or unloaded, or it's a passenger train. And you can see several spikes, so not like a clear distribution form. So if you just take the average weight per meter for the freight trains and the passenger trains, you can easily see that the freight trains can be much heavier than the passenger trains, and the passenger trains, you almost never have like a meter weight, you can say, above 2 tons per meter, whereas the freight trains can be really heavy and also really light if they don't have any goods on the wagons. So a little bit of how we determine the characteristic load to be used in the reassessment of this bridge based on the train data. So we took one of the main girders, you can say, and look at the influence line that main girder have. So we have one example here, and you can see that the influence line was around 165 meters. So this is the adverse part that you can see below the curve, and the relieving part above, but the adverse part around 165 meters, which also meant that the individual axle load wasn't that important for the what you say utilization of the girder. It was the average weight over 165 meters, which also excluded the passenger train, and we could focus more on the freight trains. So a little bit more into the data. So if we took the average UDL, so uniform distributed load over 165 meters, then if we took all trains, you can see from the data, both from the east and the westbound data, that you will get a mean around 1.5, 1.6 tons per meter. And actually a quite large standard deviation around 1 tons per meter. Whereas if we only took and looked at the tail, so you can say the 2 heaviest train per day and the 730 heaviest train per year, then we got an average around 5 tons per meter and a quite lower CVV of around 10%, so a standard deviation of 0.5. A little bit higher for the westbound than the eastbound data we also saw. So this was kind of the basis for going further with the 2 heaviest train per day, or the 730 heaviest train. Just a little bit of comparison. Then the Great Bubble Link, that train load model that was used in order to design the East Bridge, the low bridge, the west bridge of the Great Bubble Link, was a purely theoretical study where they used around 5 tons per meter and a standard deviation of 0.2 tons per meter. And previously, the assessment of the Little Bell Bridge have been used this train loads that the Great Belt also were designed for. So one of the what you say sub-scope in the analysis was also to compare these two. So how appropriate was the assumption used for the Great Belt Link. So just when we look at the 730 heaviest train, or 2 heaviest train per day, you can see from the figures to the left that there are some days where, due to some maintenance of the tracks or some other interruptions of the train traffic. There almost were no trains, and then we will have really low values, giving a really large standard deviation or coefficient of variation. Whereas if we only focus on the 730 maximum during a year, then the distribution would be much narrower and have a more tail-like extreme value distribution shape. So in order to calculate the characteristic load, we use the extended Poisson process, and the distribution that you see here would be the Fs in the formula to the right. So a little bit more into the data. So depending on whether we use the 730 heaviest trains per day or we use like a lower number, the mean value would increase by lowering the number of trains used. However, the COV, the coefficient of variation, would increase with the number of trains used in a given year. So, and here you can also see the comparison with the grade bubble length in gray. So the mean value is right around the same, whereas the COV is higher for a lot of the values. However, if you compare the characteristic uniform distributed load, then it's almost equal. And that's because the lower mean for the higher number of trains with a high COV, then that entails that you get longer out in the tail. Whereas if you have a really narrow distribution with a high mean and a low COV, then you will get around the same value in the characteristic value. So that also meant that our characteristic load was quite robust in terms of the number we picked to take into account in the extreme value distribution, which was quite assuring for us. And you can also see that when we compared with the Great Ball Link, then their assumption, even though they didn't have the same amount of data to build their theoretical analysis on, then that was also quite good assumptions. So we ended up saying that 72 or 7.2 tons per meter would be a okay characteristic load to use in the reassessment. So what's the probability of having two heavy trains on the bridge, both having like a really high average rate over 165 meters? So again, we looked into the same main girders and the same influence line, so nothing changed there. And then we looked into the meeting event, and because we didn't have data from the actual bridge, then of course it was a little bit difficult to connect in real life. So we actually did an assumption. We took the measurement station and the meeting that they had at that station and moved it artificially to the bridge and said that if two trains are just having axles on the bridge at the same time, then they would meet at the most critical location. That was we thought, I think, is a conservative assumption, but because we didn't have of the actual train, then we thought that would be okay. Again, you see the comparison with the Great Ball Link, where we have like the load reduction factor on the second track, 0.77. And we could see from the data that we will get a lower value by using these conservative assumptions, no matter how many points we were using in the extreme value analysis. So, so definitely, if we went with 0.77, that would be a conservative assumption in the reassessment as well. So one of the subscope of this analysis was also to update the reliability analysis with the new traffic load model that we, or stochastic traffic load model. Because it was an update of the existing probabilistic analysis, then we didn't change most of the stochastic distribution as input parameter to the reliability analysis. The main parameter we looked at was the train load model that we updated to reflect the stochastic model that we developed with these new data that we had from the railway network Denmark. And just I won't go into depth of that. We used a form sum analysis. You can see the sensitivities in the pie chart to the right, where you can see that it's the model uncertainty on the buckling. That's the governing together with the yield stress of the steel and the train load model uncertainty. And the conclusion for the reliability analysis was that we got above the minimum threshold of a beta of 5.2, which corresponds to a failure probability of 10 to the minus 7. We used the updated stochastic load model that we developed through data. We used the stochastic models of the resistance that were developed earlier, and the model uncertainties based on the newly published guideline for reliability-based classification of existing bridges by the Danish Road Directorate. We also looked at how the reliability index developed as a function of the load reduction factor. So the load reduction factor is in the reliability analysis previously modeled as a deterministic parameter, saying that you could use a load reduction factor of 0.77. So that was the baseline, which gave a reliability index above 5.2. But we wanted to study also what if we went up to, like, saying that we don't have any reductions on the second railway track. So having two heavy trains on the bridge at the same time. And there we saw we could almost comply. We still have a reliability index above 5, but just below 5.2, which means actually that right now Railway Network Denmark have some restrictions on the bridge of having two heavy freight trains on the bridge, that if we had like more reliable data about when they were actually passing that bridge. Remember, we did some conservative assumption of transferring the data from Bred to the actual bridge. Then it might be possible for them to waive this restriction. Yes, then we also looked in to the fatigue and the lifetime of this bridge, which of course, since it's 90 years old, is also a concern for the Railway Network Denmark. So the fatigue critical detail was already defined and identified. So it's right under the actual, what you say, tracks. So it's the crack that you see here to the right. The influence line for this fatigue critical detail, it's much smaller than for the main girders, which also makes sense. So you can see it here, and you can see that the influence lines is different from whether the train is on track A or B. So what we did was that, first of all, it was easy, of course, it was computational cumbersome to drive all the trains over the bridge and do some stress history, do rainflow counting, do Paul-Reiner's damage rule in order to calculate all the stress cycles and to ensure those. But we did that for the around 5 years of data. Then we did a little bit of probabilistic timeline extension back in time and in the future time in order to assess like how much damage has the bridge already like undergone and how much lifetime has it left. And in here you can see that the total damage, where one is like end of fatigue lifetime and the years, then you can see the different predictions. 1996, the predictions was like we would sooner reach the end of lifetime. 2012, we got a small reduction. And then now, if we look at the red one, that would say no change in traffic volume, then we got even a further reduction and a extended lifetime by more than 50 years. Then we all know that the Femern Belt will open within a few years, and that will relieve the Little Bridge for some of the freight trains, especially, which would mean that there would be even more lifetime in the bridge in this fatigue critical detail. And so all in all, very good news for Railway Network Denmark in terms of fatigue life for this bridge. Yes. Thank you for listening in. I look forward to your question at the end of this session.
Thank you, Johan. Yeah, and as Johan just said, we will take questions after Pau has done his presentation on the Little Belt suspension bridge. So please just write them in the Q&A and we'll get back to them later. So Pau.
Yes, thank you, Jan. I'll see if I can figure this out. Just wait for it. I hope you see my screen. At least
we do.
Yes, my name is Pauli Sørensen. I work in COVI, based in Copenhagen, Denmark. COVI is also a quite big consulting company with about 8,000 persons globally. My topic today will be the new Little Belt Bridge and what we have experiences with repair fatigue cracks in an orthotropic steel deck. And the agenda for today will be, first I'll give a short introduction. Then I'll talk about the bridge structure, the observed cracks we saw in 2017. I'll briefly touch on some study of repair methods, mock-up and method statement we prepared. Then in 2018, we launched a well repair campaign. Then I'll give an overview of how the number of cracks has evolved from 2017 until today. I'll briefly introduce an alternative method for crack detection by infrared camera. And in the end, I'll touch a bit upon the importance of the condition of the surfacing and what influence it has on the composite effect. And then lastly, with the summary. On the picture here to the right, we see the new Little Belt Bridge. It's from 1970, and it's a suspension bridge with a steel deck. So similar to the Little Belt Bridge of 1935, it's located here between the island of Fyn and mainland Jutland. It was opened in 1970, and it carries 3 traffic lanes of road traffic in each direction, and has about 85,000 average daily vehicles. The bridge deck is a closed steel box girder. It has a width of 33 meters and a height of 3 meters. And typically we have a 3-meter spacing between plated bulkheads. The deck structure is composed of 6 millimeter troughs, 250 millimeters height, spaced at 600 millimeters. And then we have a 12 millimeter deck plate and a 60 millimeter surfacing. At the plated bulkheads, we have cope holes of 35 millimeters. Then it's also quite important to notice that the inside of the box girder, it is protected with a dehumidification system, which I believe was the world's first. And despite having this dehumidification system, you could say that maybe the designer didn't trust it as much, because they also provided painting. So it has an orange base layer, actually containing lead, and a black tar asbestos top coat. So it's indeed very well protected for corrosion on the inside. The Road Directorate performs visual inspection typically generally every 5 or 6 years. And in the summer of 2017, we conducted a general vision inspection with an emphasis under the heavy lane and close to the expansion joints. We observed 10 fatigue cracks located in the weld between the trough and the deck plate. All of them, they were below the slow lane, which we see here, and trough numbers 14 and 16. So in this picture here, I've just highlighted the actual crack, but it extended quite far from the bulkhead, and then after around 20 centimeters or so, it moved down into the web of the trough. So these cracks were observed by visual inspection, and in order to confirm them later that year, we did a special inspection with the NDT, UT and ET that confirmed our suspicion that these were actually cracks. We also performed NDT inspections of areas where we haven't seen cracks by visual inspection, and also there we didn't observe any cracks with the NDT. So this is of course quite alarming to observe fatigue cracks, especially. Here I also have a picture of where you can actually quite see it a bit more in detail. So you see that we have this orange base layer and the black top coat. So it was possible to actually see the cracks. I would say that if the base layer had not been orange, it would have maybe been more difficult to spot it by visual inspections. But it was possible because we had this combination of paint colors. So after discovering the cracks, we did a study of repair methods, and we came up with 11 strategies. The first one was to do nothing. Then we considered move the traffic lanes about 0.6 meters, drilling stress relieving holes at the crack tip, bolting steel plates over the welds, also weld repairs from inside of the box in various forms, and lastly to replace the asphalt surfacing with a high strength concrete overlays with steel fibers. So in the end, we opted for strategy number 7, weld repairs from the inside, as we have had good experiences with this method on previous projects where we have seen fatigue cracks. So in order to repair these welds, we thought it would be very beneficial to perform a mock-up to simulate the weld repair. The mock-up had 2 purposes. First of all, it was to confirm the VPQR and VPS and the method statement. And secondly, it was to train the welder under realistic conditions. So here we see a photo of the deck plate in the correct height and the scaffold as it would be during the repair. The welder, he can then perform his weld and then immediately look from the inside what the result was. So it was quite important to perform this training, as the welder then had the opportunity to dial in his settings with regards to speed and position, etc., and then could look at it quite quickly. So the end world, they were tested both by RT, UT, MT, and macro examination, sorry. And during this trial, we also had the idea to drill 2 holes in the trough on the opposite side of the world with 16 millimeters diameter. And originally, it was intended for remote visual testing, but we found out it was actually yielded better results just to use a smartphone and a flashlight in each hole. So after working on the mock-up, we prepared the method statement with the main headlines being preparation, so removal of this poisonous paint, coordinate with traffic and NDT, then remove the crack with a grinder or rotating file, check with NDT that the crack was indeed removed, and then weld repair by TIG. So we opted for TIG welding as it has a better control of the welding, and we are not really concerned about the lack of productivity compared to other weld processes. And finally, we did NDT check to see how that we had no cracks. So in 2018, we conducted this weld repair campaign. It's important to notice that we did not close the traffic above the weld repair locations. And the campaign ended with a cost of about 6,500 euros per repair, and that was based on 10 weld repairs. Here it's worth noticing that 25% of the cost was due to removal of the paint. Some of the lessons learned from this campaign in 2018 was that it was really important to exercise great care when removing the weld and not make the gap too big. Also, we found that we could get high quality pictures through these 2 16 diameter holes. I have a picture here on the top. It's from one from the outside, and this picture it's from the inside welded, where we have the deck here and we have the trough here. So it was quite nice to actually get a visual observation of what the crack, what the welding looked like from the inside. Then I think maybe one of the main lessons learned was that it is very, very important to use an expert TIG welder that has been trained on a mock-up before doing the actual welding. Later, I think it was 2019, we also did some repairs, and even though it was the same welder who had done both the mock-up and the campaign in 2018, he still needed the training to get the settings really dialed in before going on the actual bridge. So currently, we perform visual inspections on a yearly basis. The Road Directorate has entered a framework agreement with a contractor for 3 years, and we have identified 5 types of weld repairs. The bulk of it is 70% is one called type 1, which is quite small. Then 27% type 2 with a length of 10 to 100 millimeters. And then the remaining are types 3 to 5. But the bulk of it is quite small welds. And now we have an average unit cost that is down to 3,000 euros per repair. And also the split has been slightly changed. So back in 2017, we observed the 10 cracks. We didn't perform the inspection in 2018. Then we saw a few in 19 and 20. And here in 21, you can see there's a big jump in the number of cracks observed. That is mainly because we then in 21 extended the area of observation. You have an expansion joint here, one here, and one here, and one here. And the first years, 2017 to 20, the main focus had been in the areas close to the expansion joint. But then when we extended the observation area, we see this large jump. Then we had hoped that that since the number of observed cracks it had a downtrending line, that we would be quite low in 2024. But unfortunately, we didn't happen. We had again a quite big jump. And in 2025, we haven't done any visual inspection yet. So in total, we have 157 fatigue cracks detected. So that was by visual inspection. We were quite fortunate to have this combination of paints that allowed us to see relatively clearly if there's a paint. But we also investigated if there are alternative ways of identifying the cracks. And we entered a collaboration with the Honshu Shikoku Bridge Expressway from Japan, HSBE, which has experience with detecting cracks through the use of infrared camera. So in their system, when you have the camera towards the weld, if there's not a crack, you would get a temperature profile similar to the blue one here. And if there's a crack, it will change temperature profile similar to the red line here. So in 2024, some team members from HSBE, they visited Denmark and conducted some trial tests of their technology. And we see here a differential image where in the red line there's no crack, representing this line here. And in the blue line here, you see the temperature profile, it changes shape. So by this method, they identified 3 small cracks that we had not yet observed by visual inspection. And there's some photos of their setup here to the right. So that can be quite an effective way also to identify fatigue cracks. Then lastly, I'll talk a bit about the importance of the surfacing and in regards to the composite effect. COVI has been performed a monitoring campaign of steel stresses, both for the new Little Bell Bridge and the Great Bell Bridge, which also included temperature measurement of the surfacing. And we have measured in locations both where the pavement is cracked, and then later on this pavement has been replaced to a new surfacing. So in this histogram of stresses here, we see the blue line is the cracked surface, and the red line is the intact new surfacing. And we see actually quite a large reduction of stresses due to this better performing new surfacing, the red line. When we look a bit deeper into it, considering how the stresses depends on the temperature, we can see here again that for the cooler temperatures, the new and the cracked pavement they give more or less the same stresses. But in warmer temperatures, we see a big jump also in stresses due to this cracked pavement that is the blue line. So it's really important, we think, to keep the surfacing in a good condition as possible, as it affects the stresses quite a lot. So in the end, to sum up, the new Lillebælt is a steel bridge opened in 1970. The codes of that time, it was designed in the mid-60s. It did not address the fatigue issues, but the designers actually performed some fatigue tests, and they also looked quite a bit of the history of steel bridges in mainly UK and Germany at that time. But they ended up with a deck plate that's 12 millimeter thick and 6 millimeter troughs, which is a bit smaller than the current Eurocode recommendations. We also see that when we look at the quality of the fabrication, it's clearly not as good as what we have today. We have done also some fatigue damage analysis, which I haven't touched upon here, but based on that, we will expect fatigue cracks under the slow lane in some point. So a deck type of this structure that has this detail repetitive thousands of times, it can be really, really costly to the bridge owner. And for New Lillebælt Bridge, we have about 100 kilometers of trough to deck plate wells. So it can really be quite costly. And one of the good news is that we have a good results of well repairs without closing traffic above. So that is that's good to know. And at least for the New Lillebælt Bridge, which has this combination of paints, we can see the cracks by visual inspection. But it's quite good to know that other detection methods also exist. So that was it from my part. So thank you for your attention, and I'll look forward to elaborating in the Q&A comments afterwards if there's any questions. So Jan, I'll stop sharing.
Thank you, Pau. Great presentation and very interesting. There's already a lot of questions, so I think I'll just take them from one end to the other. So the first one is to you, Johan, from Petredan, asking why was the real traffic across the old Lillebælt Bridge used? Were the Eurocode rail load models not covering real traffic, or was this a refinement to optimize the analysis?
First of all, thank you for the question. It's so more in general, working with existing structures, then in general, I would say the Eurocode give a nice framework. However, when we look at existing structures, there can be, as you mentioned yourself, room for optimization or for refinement of the analysis, simply because if we were to apply the Eurocode load for all existing structures, then a lot of them will fail in general. For this particular bridge, the Eurocode certainly could have done it, but giving a much more conservative load than that was actually on the bridge. And I think there was a need for refinement and optimization of the load in order to have room for the new service platform. And also in the fatigue analysis, it was a really nice to have the real data to work with in order to extend the fatigue life as much as possible for the client.
Yes, and one more for you, Johan from Mette Slot. What did you use as a basis for establishing the load history from 1935 until today for the fatigue analysis? That's a good question.
Yes, it's a really good question. For the first period of time, a former consultant that have done analysis for this bridge have done some study that we looked into and found trustworthy. So in that sense, we took that and applied that, and then for the newer data, we got a little bit of history from Railway Network Denmark of their view on it. A little bit of data, not really much, but some like just what you would say kind of ODT, how many trains is passing the bridge, that didn't have the data in the same detail as we had for the measurement station, but they had like how many trains had been crossing the bridge, so that we could also use. And then we had some history of which kind of train types was currently most popular in that order of time and things like that. So a mix of data and previously history and talking with the client of their input.
Yeah, great. Pau, one for you. Thank you for the presentation. Would the cracks have been very difficult to identify during inspections had weathering steel, corten steel, been used instead of coating applied over the normal steel plate? And what would your advice be when inspecting weathering steel for fatigue cracks?
Okay, so the first part is I think the cracks in New Lillebælt were quite a lot easier to detect because of this combination of paints which we had. We have after we had the paint removed and before conducting the weld repairs, it was certainly also possible to see the cracks after the paint had been removed. But I would say that it would have been more difficult. Had it been a corten steel, I would think also that it would have been even more difficult. Then, yeah, I would think so. Regarding the second question, yeah, I would suggest also starting out with a visual inspection, and then if there is some analysis to suggest that maybe that we should expect fatigue cracks in certain areas, you could perform a special inspection with either MT or infrared camera, like the Japanese have been doing. But I would say I would start out with the visual inspection, and then only if I have some analysis to back up that I would expect something in an area, I would go to the special inspections.
Yeah. Sophia is asking, is the current plan simply to continue repairing any cracks that may appear? Or is there more preventive methods being considered to prevent more fatigue cracks?
Yes. Okay, so the first part first. At the moment, yes, we'll continue with repairing cracks, any cracks that we observe. If we see a huge jump in the number of cracks again, it's certainly worth considering some of the alternatives that we looked at in the study of repair methods. we are quite interested also in this bolted steel plate solution, which is what they use in Japan to a large extent when they have similar problems. They have some experiences with bolting on steel plates. So that could be an alternative.
Yeah.
And yeah.
Another one is asking, how did you conclude that the cracks were formed only by fatigue or due to fatigue?
Well, I would say that from our analysis, we also would expect that that to see the fatigue cracks, and they did not appear to be due to fabrication issues. So we have conducted the fatigue analysis, which also indicate that we would get some fatigue cracks in that location where we have also visually observed it. So that's why we concluded it should be fatigue cracks.
Another question is from Heikki. He thanks you for the interesting presentation. And do you think that 14 to 16 millimeter deck plates would have saved the day?
I don't think that the 14 millimeter deck plate would have saved the day. When we look at the stress occurring in this cope hole, it's a bit unfortunate design, I would say, that is also not being done today. Actually, the whole details with where we don't even have the high back mouth. So the details at the connection between trough deck and bulkhead is not what we recommend today. And I think that also the stress levels that we saw in the fatigue analysis indicates that it's not a good solution. But maybe the 16 millimeter plate would have saved the day.
Yes. Johan, which information would you recommend obtaining to reduce uncertainty in your fatigue analysis even further?
Like continuously, then if I should decide myself, then having the measurement station of the data at the actual bridge in order to have the what do you say, the real data there, that would be really nice. Also, maybe we don't have that much information about the dynamic amplification of a bridge like this and how that would maybe play into the stress levels. And then, of course, if we could have a strain gauge measurement at the where the crack would be, then that would be nice. But in general, then if you're a bridge owner and I have a bridge that could at some point in time be fatigue critical, then maybe just do some measurement like of the actual fatigue. You don't necessarily have to do it all the time, but just once in a while to have some history of what have actually passed the bridge, and then it's much easier to extrapolate than leave it for the future for 90 years and then have to guess on qualified guessing on what have passed the bridge previously.
Okay, so a recommendation to bridge owners to keep all their data on bridges. Pau, I have another question for you actually. How do you, and I think it touches upon your previous answer actually, so how do you determine when it's an optimal time for repair? It's also connected with bridge safety. Could you just let it be and wait until you have a lot of cracks, or how do you see that?
So our recommendation is to well repair as soon as we see them, but bulk them in a number so that we actually have a campaign where we bulk some repairs rather than going out and repairing each one when we see it. Because it drives the cost down to, let's say, bulk some repairs, and we don't think that as such it's an issue with regards to the safety of the bridge.
Great, thanks, Pau. There's lots of questions today, so your presentations must have really triggered something. I don't know how many we have time for, but let's just try and take a few more. If you're both still here, Pau and Johan.
Yeah, sure.
Yeah. So here we have one from Peter Dan. What severity and extent were the pavement defects that influenced the fatigue cracks? And how has the condition scoring improved after repairs?
So the pavement repair, or the pavement obviously had defects. It's visible both from the top with just visual observations, but also if we drilled some samples, we could see that it was not intact, and it kind of also, to a certain extent, is maybe not that surprising. The bearing layer of the surfacing is the original one, so 55 years old, and it's due to be replaced in 2 years' time. There's a lot of maintenance activities going on at the bridge, and it just has to follow a certain planning, but it is being planned to change the entire surfacing and also waterproofing layer on the bridge.
Yeah. Another question from Amma. Do you use any fatigue monitoring methods instead of visual inspections based on SN curves or fracture mechanic approaches?
Was that for me or for Johan?
Yeah, it could be for both, I guess. You can start, Pau.
Yeah, so we have a strain gauge campaign going on at the bridge that is I think it's not running 365 days a year, but it can be turned on, and then it will deliver some data and some results, which are then analyzed, I think, on a yearly basis.
Yeah. Any comments to that, Johan?
No, well, that there's no monitoring campaign in place for the older bridge in terms of catching fatigue cracks. There's the visual inspection that they mainly rely on.
Yeah. A good question here, Pau, about how did you handle the asbestos?
Okay. Yeah, so It's not the first time that we have to remove the paint on the inside. So the Road Directorate has a framework agreement with a very specialist contractor who is specialized in removing and handling asbestos.
Great. Heike is asking, Johan, I might have missed it, but what was the dynamic amplification factor you used?
So the dynamic amplification was taking as a deterministic parameter, and it was according to the Danish rail standards for where we have two sets, one for carefully maintained and one for standard maintained track. And then there's some that's one part of it, and then another part of it is like due to the frequency of the bridge, and that will give another part of the total dynamic amplification. But there was no stochastic study done regarding this.
Yeah. And I'm just being told that if Johan and Pau have time, then we can stay online until 3:30. So that's good. It's really nice with a lot of good questions. So let's continue with a few more. Here's one from John. Pau, to you, I think. Were other solutions beyond riding surface condition identified for reducing orthotropic deck fatigue cracks?
No, I would say that it was not the main concern about the riding condition. Obviously, it has an impact on the dynamic amplification at the expansion joints, which are also due to being exchanged next year. But we didn't have any other strategies. What was it?
Yeah. Another question from an anonymous attendee asking or commenting, looks a bit risky to be to the safe operation of the bridge if we only repair when cracks are found. Shouldn't we take preventive measures to avoid more cracks? And maybe you can elaborate a bit on the other strategies you had for the bridge that you chose not to follow.
Yeah, so we know that in Japan they have rather than doing weld repairs, they have welded a steel plate over the crack as a repair strategy, which is also quite fast. We didn't go that route because we haven't seen long-term behavior of the solution that it will actually prevent the cracks from growing quite long-term. But it is a strategy that we might pursue if we see a big jump in the number of cracks. Also, HSBE has this strategy. They have been using this strategy also, so we have a collaboration with them also.
Yeah, thanks. Johan, one for you. Could current traffic data also be used in new bridge design as compared to using Eurocode standards?
I would definitely say yes, especially for the how to phrase this. Like if you look at the road traffic the one that's implemented in the Eurocode now is also based on some actual traffic data. So if you like, so in that sense, you could also use it. And what you can say it's often so that one bridge is not the only one on the network. So if you're designing one bridge, you need to look at the restriction given in the specific country and in that network, and talk with the client whether these restrictions will be maintained or will be loosened up, and what their strategy is for future traffic. And then based on that, you can definitely use today's traffic data for doing design of new structures.
Thank you, Johan. I don't know if you can hear it, but I'm in the middle of a reconstruction, so sorry for the noise. If it's too much, I'll try to mute when I'm not talking. This one is from Joshua, asking, where were the stresses measured for the comparison of damaged and repaired welds? It seems like there were severe load distributions. Do you think occurring stiffness reduction can be identified using a structural health monitoring system?
So I think that one was for me. So the stresses were located vertically on top of each other, quite close to the weld. It's not possible to put the strain gauge exactly at the weld root, but there was then fitted a slope based on the stresses down through the web, so that we had like an estimate of the stresses at the weld.
Yeah, and another one from Joshua asking if there was any service load reduction on the bridge while you were repairing.
No, there was no traffic restrictions above repairs.
What else do we have? Let's see. An anonymous attendee is asking to you, Pau, what is the type of fatigue analysis considered? Did the analysis result in a match with the cracks observed? So I think it's on whether you did like a finite element study to see if you could replicate the,
Yeah, so we conducted a finite element study with the hotspot stress method, and it was quite in line with what we saw and expected.
So we're getting there. Question from Amar. Thanks. I think that's also for you, Pau. You mentioned the bridge has around 100 kilometers of wells. How do you handle visual inspections for such a long distance? Are you thinking about using drones or similar tools to help with that?
Yeah, so you say it's a huge number of cracks, and that was also why we entered this collaboration with the HSBE to see if there's other methods, because obviously it's quite straining on somebody to perform this inspection. So it's at the moment it's being conducted visually by a team that then split it up into a number of days and a number of persons. It's not just one person inspection, the whole thing.
Yeah. Einar Teilgaard is commenting, the decks in France are 14 millimeters on the heavy lanes the last 25 years due to fatigue problems with 12 millimeter plates.
Say that's a good
and
idea.
yeah, and you would recommend even 16, was it?
No, I think maybe if it has better details than what we saw at New Lillebælt, 14 might be okay.
Yeah. David Williams is asking, does the marine environment, salt air, amplify the corrosion, fatigue interaction, and growth of cracks?
I think maybe that's for me, but in our case, we have a dehumidification system, and we don't expect salt sprays to occur inside the box girder.
Okay, I think we're almost getting there. Any last questions or comments, Pau and Johan?
No.
No.
Thank you for listening.
Yeah.
All the nice questions.
It's a good session with questions here at the end. It's nice.
And I would like to thank you as well for two good presentations. Really, really interesting and very relevant to, the asset management of bridges, and really good session. So on behalf of IAPSI Denmark, I think I will say thank you for today, and remember that if you would like to see this presentation again, it'll be online at some point. So thank you so much. Bye.